Alright, so this part of the recording is for question number 2. So for question number 2, here's the question. It's the implementation of a potentially new opcode, and this opcode, which is a mnemonic, usually has a mnemonic of RET or return, is to return control after the execution of a subroutine back to the caller, analogous with what the return statement without return value does in C or C++. The intention of this opcode is to be compliant with the caller-callee agreement that we have been using in class. And the following is representing the microcode slices to implement this opcode. Unfortunately, it is faulty. Spot the problems and fix them. So you don't want to change things that do not matter, because points will be potentially taken out, because that reflects a lack of understanding of what is important and what is not important. So there are 3 slices: slice 0, slice 1, and also slice 2. Slice 0, being the first slice, has a description that is kind of what the opcode table uses to describe what an instruction is supposed to do. So the first question is, should we enable the instruction register enable? The answer is no. Okay, so this one, I think it is safe to turn on suggesting, okay, which is a way to track changes. So we'll say this one needs to be a 0. The next question is, do we need RAM in this case? Because it's dereferencing a variable, which means we are accessing RAM, so that means RAM cell has to be a 1. And then RAM load depends on whether we are reading or writing. And because this is a read operation, 1 is correct. There's no need to change it. RI mux needs to have a specific value because we are changing one of the registers in the register bank. So what we need to do now I personally cannot remember all of those locations. So what I need to do is to start up Logisim, which you are also allowed to when you answer these questions in the test, and figure out how to configure it. This is the input into the register bank. So this is RI mux. It controls whether the input is coming from this wire or coming from this wire over here. This wire is only good if we're trying to store the result of an arithmetic operation. So it has to be the other one. So RI mux being 0 is correct. Okay, so getting back to here, RI mux being 0 is correct. RIEN needs to be a 1. And RISEL is specifying which register are we changing. So according to the mnemonic here, we are not changing register D. Register D is what we use to dereference. We're changing register B, which is basically 1 in this case. So now we need to look into register output 0 versus register output 1 and determine which one we need to use. So we need register D to drive the address port. So the address port is corresponding to this wire over here. It can be driven by the program counter, or it can be driven by register output 1. So register output 0 is not used in this case. So that means when we get back here, register output 0 can be a 0. And as a result, register output 0 select can be anything we want. It doesn't really matter. Same thing for the demultiplexer, which can also be anything. Register output 1 select needs to be 3 because we are using register D to drive the address port of RAM. And then the demultiplexer needs to be specified because we need output 0 from this demultiplexer. So a 0 is correct here, so no need to change anything. We are not using the ALU for anything, so ALU EN being 0 is good. If the ALU is not being enabled, whatever operation we specify doesn't really matter, so a 1 is fine here. Address mux needs to be a 0 because we are specifying to let output 1 of the register bank to specify the address port. So being 0 is correct in this case. PC mux is only useful if the program counter is going to be changed, which is not the case here. So 7 is fine, but PCEN needs to be a 0 because we don't want to change the program counter. ROM 24 or bit 24 of ROM, which is this wire over here, is controlling whether we're incrementing the microcode pointer or whether we are reloading it from the instruction register. So for the most part, we just need it to be a 1 to increment, and then ROM25 is resetting the microcode pointer, which means we're going back to location 000 in order to fetch again. We are not done yet because this is only slice 0 of the 3 slices. The next one is to increment D. So to increment D, we are definitely not changing the instruction register. So once again, that needs to be turned into a 0. RAM select is going to be a 0 because we don't need to use RAM for this operation. RAM load can be anything we want, can be anything in this case. Register input multiplexer needs to connect to the ALU this time. So we need this connection to the input of the register bank. So that means RIMux needs to be a 1. Okay, so RIMux needs to be a 1. RIEN needs to be a 1 because we are changing one of the registers. After all, we are incrementing register D, so register D needs to be incremented. Register input select should be a 3 in order to specify register D. And then register output 0 enable, okay, needs to be considered because in order to increment, we have to feed something into the ALU, and this is the path that we want. Okay, so register output 0 is actually going to be in use for this instruction. So our register output 0 enable needs to be a 1. And register output 0 being 3 is correct because that specifies the stack pointer, which is register D. And the register output 0 D mux also needs to be specified because we need exactly this output, which is output 1. So register output 0 D multiplexer needs to be a 1. Register output 1 select can be anything because we are not using register output 1 at all. So whatever we specify to be the output of the register bank is fine. And also whatever we specify for this particular D multiplexer is okay as well. Okay, because we are not using RAM, and we are not using RAM, and okay. Oh, okay, there we go. So this wire is actually not used, and neither is this wire, so nothing is exercised here. Now, actually, I take it back. Because in order to increment, we need this 1 to feed into this multiplexer. So in order for this 1 to feed into that multiplexer, we need to specify input 1, which means FC needs to be a 1. ALUEN is a 1 already, so that means RO1D mux needs to be a 0 because otherwise FC is not going to be a 1. Okay, so we need register output 1 demux to be a 0. It is already 0, no need to change it. ALU enable needs to be a 1 because we are using the ALU. We need to operation 0, which is increment, it's adding 1. It's basically an addition operation. Address mux can be anything because we are not using RAM. PC mux can also be anything because we are not changing the program counter. And then program counter enable needs to be a 0 because we are not changing the program counter. And then for the third slice, we are changing the program counter. So that means program counter enable needs to be a 1. And we are using register B to change it. So let's go back and change some of these things here. We are not using RAM. RAM cell needs to be a 0. And then RAM load does not matter because RAM is basically turned off. It is not selected. Register input multiplexer can be anything because register input enable is a 0. We are not changing one of the registers in the register bank. And then RISEL can be anything because we are not changing any of the registers, so it can be selecting anything. So now we have to be careful because we need one of the two register outputs from the register bank to connect to the program counter. So we look into the program counter update, okay, which is this wire, and then we look at which one can potentially connect to a register bank. It is this one, okay, because this one here, let's see, hmm, interesting. So both of these can actually be used. Um, but both of those are connected to register output 0. So that means register output 0 enabled needs to be a 1. And then register output 0 select is specifying which register it becomes the output of the register bank output 0. And that's going to be register B, which is a 1. So we need to change that to a 1. Register output 0 demux is the one that is kind of interesting because we can use either one. We can actually use this connection. So the output is coming out of 2 of the demux into input 1 of this multiplexer. But we can also use the other one, which is coming out of register output 0 from the demultiplexer into input 0 of this multiplexer. So we can actually use either one of these. If we want to use this one, then we need PC mux to be a 0 because we want this output to be a 0. Register output 0 enable is already a 1. Oh, okay, that means we don't really have a choice. Because if this is a 1, then the negated one is automatically a 0. So one of the input is already a 0, so we're going to have to use this one. So I take back what I said. Okay, we have to use the wire that we have specified here. The other wire is not going to work. So register output 0 demux needs to be a 0, okay, which is correct already. Register output 1 select can be anything because we are not using register output 1 of the register bank. Register output 1 demultiplexer can also be anything because we are not using that. Register ALU enable is a 0. That is correct because we are not adding or subtracting. So whatever operation you specify doesn't really matter because we are not turning on the ALU. Address mux can be anything we want because we are not driving the address port of RAM because RAM is off for this particular slice. PC mux we need to be careful with that because ultimately we want this wire to go into the D port of the program counter. So that means PC mux itself needs to specify 0. And in order for PC mux to be a 0, we can select either 5 or 6 for PC mux. So now we go back here. So this can be a 5 or 6. So you only have to choose one. Okay, if you want to specify 5 or 6 will work, that is fine as well. So that concludes the third slice. So for this particular question, there are several ways to do this question relatively quickly. One way is to look into this particular slice, which is really doing the same thing as an LD instruction. So it's LDBD is doing the same thing. So we can use the assembler to assemble this particular opcode and then put it into the microcode pointer over here. So that will basically go to that particular slice, and from LogicSim you can actually see which pin or which tunnel is a 1, which tunnel is a 0, and so on. So it will give you some idea of how to answer the question, but it won't tell you if there's an inconsistency, if there's a difference between these numbers and what you see in LogicSim, then you really have to think whether that is that needs to be changed or not. Because if a particular signal does not matter, you're not supposed to change it. So that really is the tricky part of this question is people who make unnecessary additional changes will get points deducted, because anyone can copy and paste from Logisim, after going to the slides of LDBD in this case, or increment D in this case, and also JMPB in this case. So it's easy to make a copy of whatever you can observe in Logisim, but understanding when when there's a difference between what you see here in these slices and what you see when you inject the opcode into the microcode pointer, that requires understanding of how the processor works. So that is that's probably going to be the tricky part of question number 2. So after question number 2, let's move on to question number 3. I can combine the recording into one, because question number 3 is actually probably the most straightforward question of all the questions in this exam. So it is true that I put it, as the last question, but it was not because I wanted to trick anyone and put the easiest question as the last one. Because I on day 1 when I talked about the syllabus, I already told people to basically evaluate every single question at the beginning of a test, figure out which one is the easiest, work on that one first, and work on the next hardest question, and then leave the hardest one to be the last question. So let's go ahead and take a look at this one. Okay. All right. So this is basically asking for a hexadecimal representation of all the excuse me, let me pause the recording, except there's no pause button here, so I'm just going to be back in a few, maybe 20 seconds. All right, I'm back. All right, so reading the question, you're converting a value to a double precision floating point number in hexadecimal. So that's representing the binary zeros and ones, but in hexadecimal, and use the following space to derive the result. Okay, so there are many ways to do this. Okay, this is just one of the many ways. So you want to break up 17 into a sum of powers of 2. You can make it like this, okay? 16 plus 1 plus 0.5 plus 0.25, okay? Because those are all powers of 2. But I need to see that you know how to convert between base 10 and base 2, okay? So some steps has to be shown instead of just, quoting the numbers, okay? But in my case, I cannot, just look at these and figure out the actual bit pattern. Okay, so I'm gonna have to use one more step here. So 16 is 2 to the power of 4, which is 1, 0, 0, 0, 0, 4 zeros in base 2. 1 is fine, it is just 1 in base 2. 0.5 is 2 to the power of negative 1, which is 0.1 in base 2. And then 0.25 is 2 to the power of negative 2, which is 0.01 in base 2. Okay, so now I look at this, and okay, let's not forget the equal symbol here. So now we look at this and just kind of line up everything. So we have 1, 0, 0, 0, 1.11 in base 2. Okay, so now we know what the number looks like in base 2. And implicitly, there's a times 2 to the power of 0, right? So there's a implicitly times 2 to the power of 0 in here. So now we have to do the conversion again, okay? So because we want the mantissa to be normalized. So that means, if I were to do this step by step, which I personally prefer because I cannot track minor details. So I need to do this step by step. So I can shift 4 times. So 1, 2, 3, 4. So that's 4 times. So I will shift this point to here. But in order to make up for the change in terms of magnitude, the exponent of 2 needs to be incremented here. And from here to here, we'll increment again. But then the point will now be shifted over here. And then we have 2 to the power of 2. And then from here, we'll put the point right here. And the power of 2 should now be 3. And this one obviously should be 4, and then the point is going to go here. So I'm step by step shifting the number. Now if this test was done, oh, I forgot to erase one extra point over here. So if this test was done using pencil and paper, I can kind of see why this is kind of wasting time and why some people may not want to do it this way. On the other hand, if this is done using Google spreadsheet, Google document, copy and paste is really quick and easy, and it really helps to eliminate any errors that we might be making, or at least if I were to look for ways to give people partial credit, this will give the instructor plenty of opportunities to assign partial credit. So now that we have this conversion, then we basically specify the sign is 0 because 17.75 is not negative. Okay, the exponent takes an extra step because e2 is 4 because we calculated that over here. Oops. But e itself, okay, the actual value, from bit 62 down to bit 52, okay, those 11 bits, they need to represent a value that is that's offset, okay, that's offset by 1023. So 1023 plus 4 is what that bit pattern needs to represent, and that is 1024 plus 3. So there's a 2 and a 1 over here. So once we convert it into binary, it is 1 followed by 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in base 2, plus 2, which is 100 in base 2, plus 1, which is 1. Oh, okay, 2 is 10 in base 2. I just got 1 0 too many. Okay, so once we combine all of these ones, then we have 1, and then followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and then 1 1 over here. And then the mantissa is the fractional part of the number, so the 1 point is not included. So that means we are only starting with 0 0 0. So let me point out which portion we are talking about. So we are starting with this 0 0 0 over here because the 1 point is implicit, and then we have 1 1 1, and then the rest of the mantissa are all zeros. So when string everything together, okay, it becomes 0 for the sign, 1 followed by 8 zeros, 1 2 3 4 5 6 7 8, 1 1, and then 0 0 0 1 1 1, 0 0 0, and the rest are all zeros. Okay, so as a double representation in binary, it's going to look like this. And then we'll group the bits into groups of 4. Okay, so we have these 4. So if I were to really show step by step, I'm gonna just copy and paste, and then this time I would use some extra spacing here to indicate how the bits are separated, like so. Okay, and once the bits are separated in base 2 into groups of 4, then I can look at each group of 4 bits and then say this is 4, this is 0, this is 3, this is 1, this is C, and the rest are zeros. Okay, so now we can say the hexadecimal representation of the double floating point number is 0x4031c, and then we have 11 zeros in this case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's how I would answer this question. Um, so that's really just step by step. The grading criteria for this one is fairly straightforward. It's just, do we know how to do the conversion into base 2? Once it is in base 2, do we know how to shift the point to the right place and make adjustments to the exponent of 2? And then do we know how to add how the sign bit is determined, how the exponent is determined, how the biased exponent is determined, and how it turns into binary, and then whether we store the mantissa including the 1 point or not including the 1 point. So concatenating everything, and then we chop the bits into groups of 4 and then convert each group of 4 into a hexadecimal digit. So that basically is the quick summary of all of this stuff here. And the best part of this particular question is if you make a mistake, you can actually use the technique that we talked about in class and check and see whether you made a mistake or not. So just to repeat that experiment, okay, that we did in class, we'll just rewrite that program, right? So we'll have a q3.c, which include pound include std_int.h, standard integer.h, and here's main, and then we have a uint 64_t, which is a 64-bit unsigned integer. Okay, we call it x. X gets 0, so the compiler does not compile the local variable x away, and then just return 0 over here. Okay, that's the program. And then we use gcc-g to include debug information -o q3 to specify the executable name, and then q3.c to specify the source file, gdb q3, list the program, put a breakpoint on line 8, run the program. So now we have x to play with. So we can now say set var x equals 2 0x 4031c 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. All right. So now we have to use the trick that we talked about in class, which is casting the address of x into a address of a double, and then dereference it as an address of a double, and we get the result back. So this is just a quick and easy way to verify the result. Okay. And then somebody is going to say, oh, that means we can also use the same technique to answer the question, right? Because you can reverse the process. So let's just say that the value that in your question is I don't know, 100.25. Okay. So what you can do, what some people would do, okay, is to say set var dereference cast pointer, okay, and then we specify, what was it again, 100.25, I think. Okay, so you basically perform this process in reverse. Okay, then you can print x out. Now this is definitely not how we want it, because we want to print it in hexadecimal. So you can say print /x, I think, x here, and this is in hexadecimal. So someone can say, well, I can use this process and figure out the answer is 0x40591 and then a whole bunch of zeros if the value to be converted is 100.25. If somebody gave me like a screenshot or just a copy and paste of this part here into the answer, that answer would either get no points or it's going to get a very low amount of points, because it is not demonstrating that that person understands how to do it manually. Because the test is not testing whether GDB can do this, it's testing whether the person who is answering the question can do it or not. So that is why in the question it was very specific to basically do it step by step. Okay, so if there's no step-by-step, demonstration of that person knowing how to do this. There'll be either no points or it'll be a very small amount of points, for that particular answer. So that kind of addresses all of the questions of the exam. I didn't know, how I didn't. hmm, I thought the test was not very challenging because originally I was thinking about having the same usual amount of questions for exam two, which is 5 questions or so, and I only had time to generate randomized questions for 3 of them, and I thought, oh, okay, I just couldn't finish the whole exam because I was targeting 5 questions and I could only make 3. So I wasn't anticipating people to think the test was a little bit challenging, because even though question number 1 is a little bit more time consuming, you know for someone who understand the concept, it really is just a matter of going through, okay, make all the recommended changes, and that one is fairly easy to have partial credit, because even if someone cannot finish or spot every single problem, if they can spot some of the problems, I can say, well, this person seemed to have the knowledge of how um, C to assembly language translation works, even though it may not be able to catch every single problem that is in the problem. So anyway, this is the end of the recording, and I will see you guys in class tonight.